You have to work. So your room doesn't just clean itself up unless it's a Disney movie, right? Now, sometimes people object to that kind of a definition because they're like, no, it's not macro examples like that. It's really energy states. And your book has some very nice descriptions about why, if there's more randomness or more disorder, there's more spreading out of that energy. But sometimes it's just helpful to think about, like, what's more likely if a glass falls off of here. It's more likely to break into 1,000 pieces than those 1,000 pieces will just put themselves together, right? So very often in our real life, the random processes, the disordered processes, are the ones that are more likely to occur, okay? Alrighty, so if something goes from a solid to a gas, we would call that an increase in entropy. Why? Because in a solid, okay, if I have this little cube of a solid, they're just vibrating there, right? In their little place, they're vibrating. And there's only so many states or microstates where the energy can be distributed. If you think about a gas particles are all over. And there's way more energy states, microstates, where the energy can be distributed. So depending on how much math you've taken, you can tell that this is starting to be kind of a mathematical collection of these various energy states for various systems. And you can all, I know you're all sad that we have to calculate the pH at the equivalence point, but you can all be happy that we don't have to integrate all the microstates and figure out exactly how many of them there are. So that is one small consolation. We're going to talk about this randomness or disorder in a system. We are just going to talk about entropy in terms of some definitions, so I don't want you to be like just waiting for like, so what is it? What is it? All right. One brief other comment before I talk about the third law. You may recall that when you did energy before, there were standard enthalpy and they were constants. There was a certain kilojoules per mole. So there was a certain number of kilojoules that it would take to form a certain compound, right? And so how did you calculate these? You calculated them as making 1 mole of a substance. So this is not the way we would normally write the reaction for water. But because we want to have a standard heat of formation for water, and since enthalpy is a state function, somebody from on high decided that all the elements in their standard states would have what? Does anybody remember what their enthalpy is? Anybody? 0. It's 0. And so then what do? We measure the change in energy to make water from this much oxygen and this much hydrogen, and whatever that value is the standard heat of formation for the formation of 1 mole of water. You guys remember that at all? Okay. It turns out that entropy is not that way. The third law tells us that the entropy of any perfectly crystalline solid at absolute 0 kelvins is 0. So also as review, can you get any colder than 0 Kelvin? No. So 0 Kelvin is what we call absolute 0. So what they assumed as far as having these entropy values for substances is that everything starts as a perfect crystal solid at absolute 0, okay? And so all entropies, all change in entropies are positive. So all delta S of formations are positive. There are no negatives. If you remember that we could have enthalpy, standard heats of formation for some substances that would be negative, some would be positive, right? That's not true when you have a standard value for a substance. They are all positive. Why? Because they start at 0 and they go up as temperature rises. And why is that? Because what's happening as that perfect crystal is getting, is increasing in temperature from absolute 0 is that, excuse me, the crystal first gets more disordered, right, as the temperature rises. It's not a perfect crystal anymore. Finally, you're going to get to the point where it would become a liquid, and that's much more disordered, okay? And then it would become more and more and more disorderly until it becomes a gas, okay? All right. So those are the 3 laws of thermodynamics that all of our work in thermodynamics is governed by. So here's a review of some of our thermodynamic terms. I've already used some of them probably. The system is the part of the universe under study. All of these should look familiar. The surroundings are the rest of the universe excluding the system. We've already talked to us about a state function as a quantity whose value is determined only by initial and final states of the system. And standard conditions, pressure equals 1 bar. I've also seen 1 atmosphere. Solution concentration equals 1 molar. And standard conditions are represented by this little naught sign, which I've also already used. So there's just a collection of the definitions that should be reviewed, and if they're not, you should definitely possibly consider doing some review. Because those are words that you will have to understand. So, for example, if you are I lost my train of thought. Okay. Any questions about any of those? All right. Here's where we technically define, enthalpy is defined as that internal energy plus our work here in this particular case is what we call pressure volume work. But remember, we said that we were going to keep the pressure and the temperature constant. And so our delta H is just simply equal to our energy for our small little place in the world. Now, if we have a chemical reaction, we can calculate the standard change in enthalpy. Remember, this little thing is just a summation. This refers to the coefficient in front of each number in the balanced chemical equation. For the products, this is the summation of all the reactants. And here's the coefficients that are in front of each one of those.